All right, welcome back. Today we are talking about rolling. And again, just like with torque and rotational dynamics that we talked about yesterday or in the last set of videos, rolling is an extension of something you already kind of know about. It integrates forces and energy, and it adds into that rotational motion. Okay, so some of the problems you're going to see will look familiar, but now that we're integrating rolling in, there's going to be like an extra step or two. So what do we mean by rolling? What is happening when an object ends up rolling? Well, the majority of the problems that you will see will be talking about when an object, what we call rolling without slipping. If you think about it, there's really three ways that an object could move over a surface and also have some rotation. It could roll without slipping. Let me move some stuff here very nicely so that, and I hope you can see this, this would be rolling without slipping, okay? The ball is not slipping. It's not, I guess it'll make more sense when I show you the other two cases. This is rolling without slipping, just what we normally think of as rolling. We could have rolling with slipping, where even as the object is rolling, it's also rotating more than it would otherwise. In other words, there's not a lot of friction between the contact point and the surface, so it slips. Okay, it slips, it's going a little faster. This is kind of like when you are at a stop sign and you try to accelerate a little too quickly, your tires spin. That's rolling with slipping. I guess the one other example that we could have is rolling with skidding, which is kind of like if you're coming to a stop sign really quickly, you slam on the brakes and your wheels should lock up, your tires should skid, but they're also probably rolling forward a little bit as well. That would be rolling, I guess, with what I would call skidding. What we focus on is rolling without slipping or skidding, where if you notice, the contact point of the object that's rolling, when it is in contact with the surface, is momentarily at rest. It's not translating side to side. That one little tiny point that's in contact is momentarily at rest, okay, relative to the surface. That's what we call rolling without slipping. Contact point between object and surface is momentarily stationary. Doesn't mean the object is stationary, it just means that one little point relative to the surface is stationary. And if an object is rolling without slipping, clearly the object is translating, it's moving from place to place, and it's also rotating. So this type of object has both translational and rotational kinetic energy. And we talked about this a little bit yesterday. We talked about how to find the rotational kinetic energy for an object. Let's talk about that in a little more detail. Energy when something is rolling versus the energy when something is just sliding along. This would be sliding, okay? No rotation. Rolling, it's translating and rotating. So for a sliding object, if it's not rotating, this is what we've dealt with for the majority of the past 2 years. Oops, sliding, not rotation, I'm sorry, sliding object. We know that for a sliding object, so one that's simply translating, the kinetic energy equals 1/2 mv squared. This is important because this means that all of the kinetic energy is involved in, I guess I'll say, getting the object from point A to point B. And what happens here, maybe you've never thought of it this way, this makes the object go pretty fast. All the energy is involved in getting the object from point A to point B. So it goes fast in this situation. Now, for a rolling object, that's going to be a little different. For an object that's rolling, The kinetic energy, it will obviously move place to place. Okay, it is moving side to side. I guess you could also have a situation where you just have an object that's spinning in place, but that's not what we're talking about here. We're talking about something rolling. The object is not only translating, it's also rotating. So the kinetic energy is not only dependent on the linear speed, but it's also dependent on the angular speed, the speed of rotation. Okay? This is the translational part of the kinetic energy. This is the rotational part of the kinetic energy. Now, what we're going to do here is we're going to compare this. Oh, some sort of siren outside. What we're going to do is we're going to compare these two, and we're going to see how they compare. What I want you to do is I want you to call the relationship between linear speed and angular speed. Remember that linear speed is equal to the radius of the object, or the radius of rotation, multiplied by the angular speed. What this means is that the angular speed is equal to v over r. Now what I'm going to do with that is I'm going to plug this in here, so that now I could say instead we have 1/2 mv squared plus 1/2. Remember that for the moment of inertia, for an object that is for some object, it's always going to have the form some coefficient times the mass times some distance, usually a radius or a length, squared. And now I'm going to plug in for omega, v squared over r squared. Okay? I've just written these, I've written I and omega in terms that might be a little bit more familiar. Remember, a is simply a coefficient, it's not acceleration. If you look here, I've got an r squared up here, I've got an r squared in the denominator. Those will cancel out. So here's what I'm left with. I have 1/2 mv squared from over here plus 1/2 a mv squared. And if you look at this, the only difference between these two terms, this one has an extra factor of a. I'm going to factor out the 1/2 mv squared part. Here's what I'm left with. 1/2 mv squared, in parentheses 1, plus a. So this has kind of an interesting little meaning to it. What it means is if you have an object, if you have one object that's sliding, one object that's rolling, and they have the same linear speed, because the one that's rolling has this extra coefficient of a, which is always going to be positive, if they're moving at the same linear speed, the one that's rolling will automatically have more kinetic energy. Okay? So, it takes more energy for an object to roll at a certain speed than slide. If it is rolling at a certain speed, it will be moving. If it's rolling at a certain speed, it will have more kinetic energy than if it was sliding at the same speed. What this also means is that kind of the opposite. If the kinetic energy that the object has is the same, whether it's rolling or sliding, so in other words, if you give two different objects, let's say 100 joules of kinetic energy, one of them is sliding, the other one is rolling. The rolling object is slower. So make sure you understand the difference between these two scenarios. If we have two objects, one is sliding at a certain speed, one is rolling at a certain speed, the rolling one will have more kinetic energy. If, on the other hand, we make sure the objects have the same kinetic energy, the one that's rolling will be slower. The reason it will be slower is that some energy that would have gone into translation is used to make the object rotate. And that's actually really important, okay? If two objects have the same kinetic energy, the one that rolls ends up being slower than the one that simply slides. And I don't think that's something that's very obvious if I were to just ask you off the top, out of nowhere, like, hey, which one of these objects will be moving faster after it gets down a ramp or something like that. It's kind of an interesting result. We're going to really focus on that as we go through these notes in this tutorial, because it is a problem that seems to show up a decent amount on the AP exam. So, we talked a little about what rolling without slipping means. We talked about the energy that an object has when it rolls as opposed to the energy it has when it slides. What we're going to talk about now is how friction plays a role. And as I was looking at this yesterday and this morning, and trying to think of, kind of refreshing my memory on how all this stuff works, I was struck by this example. And the example I have here, it's a good example, it's correct. Okay, it's a correct example, but friction, as you probably noticed when we were doing the unit, when we're doing our forces unit, friction is tricky. There are some things with friction which are very hard, not very hard, but friction, there's not usually like a set of very structured, hard and fast rules for friction. It's really, really dependent on the situation. So I'm just going to give you one example here of how friction could play a role in a certain scenario. Then, when we go to other problems, you're going to get another example of how friction can play a role, and they're actually different. Okay, but it's still, it's logical how it works in both cases. You really have to understand the situation. So, here's our case here. Let's imagine, this is more about, the example I'm going to give here is like, how does friction play a role, let's say, with allowing a car to have its wheels start to turn and roll on the ground. So what we're going to do is imagine an object, and we can even write in car tire. And that car tire is spinning on a surface, and that surface and the car tire, there's a coefficient of friction between them. Okay, so here is our surface, we have our tire, and the tire, due to an internal torque from the engine, is being made to rotate in this direction. So, when I deal with friction, I always give the advice of imagine what would happen if there was no friction. If there was no friction for this car tire, then essentially what would happen is at this contact point, there would be no force to resist the tire's motion. It would simply spin in place. And relative to the ground, the point of contact with the tire would move to the left. Okay? From the ground's perspective, the point of contact with the tire would move to the left. Well, there is friction. Friction tends to oppose the local motion, the motion in that particular area. If the tire would move to the left, or not the tire, the little tiny piece of the tire in contact with the ground right here, if that would move to the left in the absence of friction, well, then that means that friction must, in this situation, act to the right. Okay? So, I just want to make a little note. Another force, note the torque from the motor, another force will cause the initial rotation here. But if there was no friction, then this rotation would not end up moving the car. There we go. Looks a little bit better now. Okay. So, as we just discussed, the point of contact between the tire or the wheel or whatever and ground moves left relative to the ground. So from the ground's perspective, that's what that means. And because this happens, therefore, the ground exerts force of friction on tire to the right. This is actually the force that allows the car to move forward. We don't often think of friction as causing things to speed up, but in this case, friction is what allows the car to kind of push off and move forward and accelerate. Okay? It is actually the force of friction that ends up propelling the car forward. Which is very interesting. The alternative case, if there was no friction, tire and car, they end up, well, they don't move forward. And what happens is the object will simply, the wheels will simply spin. Friction allows it to translate forward in addition to rotate. Okay? Now, again, that's one example for a car. There are other cases where friction will, as we're used to, act backwards on an object. Matter of fact, the next example, we'll see where friction acts backwards. And that, again, is because of the situation here. This is a different situation than what we will see in just a few minutes. Actually, I'm going to stop that right there. I'll do the next one on the next video.